Welcome, everyone. Thanks for coming. We appreciate your being here. My name is Sean Walbridge. I'm a Python developer on the Pro team. I work on a few other areas of the product. And this is my colleague, Kevin Butler.
I work on the spatial stats team, and I'm not so pretentious that I have to use my middle name, except there are two Kevin Butlers at Esri. So if you see some great writing and some great raster analytical work, it's the other Kevin Butler.
Versus my name, where there's only like about 4 of me in the world.
Yeah.
So I usually am okay. So one thing we always try to do with this talk is we put all of this up in a Github repository. This URL is a lie right at this minute. I haven't uploaded it yet, but I will immediately after this. The reason I'm telling you that is that if you want to just write down this URL, it will save you from some furious writing at other times. There's a significant amount of links and links to resources in this talk, and this is a helpful way for you just to be able to get all of that afterward. Sometimes I'll be searching for something on the internet, and I will find a previous version of this talk that I did previously, and I'm like, oh, thanks, previous me. So hopefully it also will help you with your work. But even if it doesn't, I'm still happy. So it's not so bad either way. So yeah, that's the. Can you all read that? Is that okay? Is that big enough?
Yeah, it's good.
Okay. All right. So it's github.com/SCW/DS-SciPi-DevSummit-2019-talk. And I just realized that's way too long of a URL, so I'm sorry I didn't shorten it. But yeah, so we'll put this all up here. We have a few code examples and some notebooks that we're going to be showing you today, and we'll make sure those are up there as well for you to access. Yeah, I guess with that, we'll get started. Okay, so this is always the perennial question. What is data science? We have a lot of people in our community who do geospatial work who, maybe 5 years ago this label didn't exist, and they would say that they're analysts or they are geospatial programmers or scientists or developers. Data science, it has 2 parts to it. There's a real change in how people are doing work, and there's it's the new cool hot job, so things get glommed into that whether or not they're actually new, right? And that's not uncommon to see. One way that you can connect this is to to an existing model. One of those existing model is this kind of more like scientific computing model. Like, what are all the things you need to do in order to carry out science?
And this is not necessarily a new topic. This came out of Microsoft research, this idea of doing e-science. And we've always used computational methods in science, at least in my lifetime. But the thing that makes this difference is now that there are computational methods involved in all of the different aspects of science, all the way from data acquisition to visualization to actually sharing research and analytical results. So computational science, data science has permeated all aspects of what we used to call the scientific method.
Yeah, and one thing too that I think anyone who deals with spatial data that one of the things data science makes this claim of is 80% of the work is cleaning the data. Well, if you've done any work with geographic data, you know exactly that story, right? It's really not easy to take data coming from some source and understand its error properties, understand what's going on, and extract the real meaning out of it, right? And that's always been the saying that 80% of all data has geographic context, but it's not always bubbled up in a way that's useful. And I don't mean by that you're using a database that doesn't understand the curvature of the Earth. It's even just down to the simple, how do I represent this in a gazetteer, or how do I represent this continuous phenomena and deal with that in an accurate way. So another story that has become important is this idea of extending ArcGIS, right? You have ArcGIS as this system of record. It's taking data from all these different systems and combining it. And we're always adding to it. It's getting bigger all the time, and if you go to other sessions, you'll see all the things that we're doing to make it better and to improve it in many different dimensions. But it still can't do everything, right? It always has a bounded set of computational capabilities it has. It can only do so much in many different areas. We have over 1,300 geoprocessing tools now, and that would be compared to maybe like 500 or 600 5 years ago. So it's growing very dramatically what you can do with geoprocessing tools, with Python, with all these different things. But we also recognize the importance of enabling integration with other systems, with other environments, and the ability to extend the platform across different dimensions. So you're seeing that in a lot of different ways. One is that we are doing more to allow you to use this talk is mostly focused on the scientific, the Python scientific computing stack. That's one of the main things that we have. We have that in a lot of different places. But you also see this in just next door, they just wrapped up a 4-hour workshop on R, right? So we have a story for integrating with the R statistical language. And we have pieces of our stack now that are integrating with the Spark ecosystem. So if you use GeoAnalytics server, that's Spark-based. So you start to see this very integrated story where all these different pieces are getting coordinated. And we're not going to go into a deep dive on this, but we also are putting pieces of the software stack in that really enable you to extend it in different ways. So one of those that I'll show really briefly toward the end is something called Conda. So that's this package management system that ships in Pro, it's in server, and it's also the basis of the hosted notebooks that you may have seen earlier in the week. So we are doing a lot of different things that kind of align the work that you already know and already are doing to make you, if you want, you can go and take down that hat that says spatial data scientist. Now, I'm not saying that you should just be like, yes, I'm going to call myself whatever, give me more money. Well, you can do that too. But what I'm saying is that there is a lot that you already probably know, and you already have a lot of expertise in this domain, whether or not you have that label. There's, of course, the depths of statistical understanding that typically is implied by data science, but that you shouldn't feel like it's some special group, right? There's this the joke is that what's a data scientist? A data scientist is a statistician who lives in San Francisco. And that I think that's becoming less and less true, right? It's becoming less of a meaningful joke because we're accepting this as a new role in science. And as Kevin mentioned, there was a book Microsoft wrote about 10 years ago called The Fourth Paradigm about the changes that computation brings to science. And it's just a reflection of that broader systems change. So if you do things and you've been doing this for a while and you've had different labels, think about it. I mean, there's things that you might pick up in becoming more of this kind of data scientist role. And we think that Pro can really help support you in that. And we're working on making sure our stack supports you in that kind of change. Okay, so like I said, we're really kind of focused today on Python. So I'll just give you a really brief background on Python. Many of you probably already use it today in various capacities. So it's really popular, right? This is a nice thing. When I was learning computer science, it was like, oh, here's 4 different languages that no one's really using that you need to learn as the gateway into doing anything. Well, now you're seeing in lots of different areas, in a lot of domain sciences, they're teaching Python out of the gate. And there's a lot of different reasons for that. One of them is that the friction to using Python is much lower than many languages in the past. So the amount that you have to take on in order to actually start writing productive Python code is lower. And there's a lot of little consistencies in the language, which mean that once you've learned how to do some basic things, that translates really well into learning new libraries and learning new things. In many languages, other languages, you learn a certain model, and then you go to some other code, and you're like, what the heck? I already learned this whole model. Why is this completely different? They don't translate well. And if you saw our Python across the platform talk, I equivocate this to like the Neo moment of like, I know Kung Fu, where he just downloads into his brain all of Kung Fu. And what I mean by that is that you learn how to write Python code, and then if you go to a new code base or you're collaborating with someone, there's a certain set of shared understanding about what makes good or Pythonic code, and that really lowers the barrier to you learning new interfaces. And that's important both because not all of us just want to geek out in programming land all the time. Many of us are domain scientists. We have expertise in specialized areas. We want to be able to jump in, be productive, and then get back to the actual analysis question. And it's a helpful thing for that. So in part because of that, you've really seen Python grow dramatically as this glue language to bind together all kinds of things. And one thing to note here too is that Python, part of the glue language story is that it's being used to access libraries written in other languages. So when you use, if you use, like I showed a demo earlier of GDAL. GDAL is a C library, a C++ library. You can access it through Python. That means you don't have to learn C to do that. And that's the story in many different places. When you actually use ArcPy, ArcPy itself is implemented in C++, but that's immaterial to your use of it from a Python perspective. And that's meant that many of these existing code bases can just provide a Python interface to their underlying implementation, which might be done in some other language. And if you look at what's happening with the machine learning space, things like TensorFlow, you're seeing that same exact pattern. They are providing the interface in Python because of its kind of lingua franca for data science, but the actual implementation might be in some other language. And the last thing, it's open source, right? We like that.
Yes.
It's great. We can take our work, we can take our skills and use them in other places. Okay, and at the end, I have some resources that kind of talk about things you could do to get started in the space, or jumping off points. One of the things that's really important about the Python community is its community. And by that I mean both the amount of resources that are available online, but I actually mean even more than that, the human aspect of this. If you have a chance and you're interested in Python, I really recommend going either to a local or regional Python conference, or there's also one called PyCon. It's giant. It's not quite to the UC scale, but it's maybe like 8,000, something like that, 8,000 people. And it's really impressive. It's Python used in every possible area, lots of things you never would have thought of. And there's a really strong community of people who work on this language, and they're very open. And yeah, it's a special community to get to participate in.
There's also the SidePI conference.
Also the SciPi conference.
Yeah.
So if you're into the science, if you really like Jupyter notebooks, or if you like any of the libraries we're about to show you, go to the SciPi conference, because you'll get to meet the people there and talk to them, and they're just normal people, and they're not they're not doing crazy book signings or anything. They'll hang out with you and talk to you, and if you want, you can have a beer with them afterward. Okay, so Python and ArcGIS, it's been around for a long time. It's this API for driving a lot that happens in the desktop space, the server space. We have ArcPy. I won't belabor the point of all the things you can do, but we added just a few years ago the ArcGIS API for Python. Also emergent is this new hosted notebooks platform. And the hosted notebooks platform we're not going to get to in too much detail today. But one thing to know about that is that all the work you've already learned, all the things that we're going to show you today, are also applicable in that context. So it has ArcPy, it has the ArcGIS API for Python, and it has 200 odd other libraries in it, many of them machine learning and data science focused. But there's a reinforcement here, right? We try to make sure that the things that we show you are things that make sense, that they resonate with what you already know, and you're continually able to take your existing skills and translate them to new spaces. So hosted notebooks, even if you don't, you're not going to live there, you're not about, I want to access Python from my iPad, it does mean that now you'd have a deployment target for your code, right? You could give it to someone else and it would be shareable and they could edit it, and you have a new way of interacting with code that wouldn't be possible just on your desktop or server alone. I don't know what happened to that last slide, but that's not important. Looks like the axis is cut off at the bottom here, but I'll come up here and quickly. So this is where we start out. We start out, 2004, that's our beginning. This is our 15-year trajectory in Python. We've got a decade and a half under our belt now of interacting with Python. So started out, it was just one of 3 possible language bindings. 2 years later, we kind of said, okay, people just want Python. Turns out they didn't want VB. Who knew? But we kind of standardized on Python, and we started including libraries. This chart here is the number of packages included in our base distribution. So that's a distribution that's in Pro. that's in the server environment as well, in the Pro runtime environment. We added it to server, and you get ArcPy, and you see this trajectory is great. There's a lot of really cool stuff happening here, right? And I just labeled some of the things that are Pro specific, since we're kind of focused on Pro today. But we're doing a lot in this space, and there's some even more exciting. I'll show you a couple exciting things at the end that are coming up soon. But there's a real growth here, and a lot happening. And the number of packages, we can only show you a few of them, but check out that list, see what you're interested in, and let us know too. If you say, hey, it would be really useful for me, I have this set of 1,000 machines that I'm helping maintain. If you could help get this package or that package in, we can talk about that. We're always interested in hearing where this doesn't serve people. Okay, so SidePI. So the SidePI, where did I go with? Confusing myself here. Okay, so I did have a Scifi Stack. So yeah, so this is one of the things that makes Python so great for a lot of the kind of more scientific problem solving, is that it deals with the data types that are necessary for scientific computation. So it's not always that you just want these object-oriented programming methods. You want other approaches, and SciPy kind of takes a few different tacks. One is the SciPy stack takes a few different tacks. One is that it provides you with really great primitives for building up scientific computation, things like vectors, complex numbers, statistical operators at a low level. But it also is binding into things to make this all just work. And what I mean by that is when the library called SciPy, for example, it includes a Fortran compiler, which sounds like a horrible thing, but I promise you it's actually not that bad. That means that you could take some Fortran code. Fortran code actually, it's something that people have from like the 60s and can still run today. And there's not many languages that have that same thing true about them, and modern Fortran doesn't maybe look as bad as what you've seen in the past, where it's all angry, all uppercase. It's got a lot of nice features now in the language, but so it's kind of one of the ways it's been integrated is it's pulled in all these different things from other ecosystems and kind of made it all fit together. So this is the basic SciPy stack. The SciPy stack has been around for about maybe 5 years now. So these are kind of the core libraries that make up the base of the scientific computing stack. So this is some of the things that enabled the ability for Python to be really useful for scientific problem solving. So we'll talk about some of these in more detail in the coming slides, and some things that aren't included here as well. And I forgot to fix this slide, so I will fix that before I send it to you. You can't really read this, but the idea here is that besides there just being lots of really big numbers, you can see that there's a lot of people involved, right? This is the number of unique contributors on each of these projects. So some of these projects have thousands of people contributing to them. Now that might be someone just drive by, typo fix, but a lot of these people are doing this, they're using these packages every day in their work, and they're committed to improving it. This is partly what I mentioned when you talk about community, right? If you go and look at these code bases, you can see what's going on, you can file bugs, and you can help out and become part of that community. It's kind of a cool thing. And these stars are just it's the like button of GitHub, so it kind of gives you a sense of how popular these are. But you see, that's a lot. That's a lot even in probably like the top of any GitHub projects, like maybe like 60,000 stars or something. So it's a lot of people who are interested in some of these libraries. Okay, and we're not going to go into detail on all of these. There's some that we just want to kind of put out there for you, and then we'll zoom back from. We think they're interesting. One is this Simpie. So Simpie, if you ever use something like Mathematica or any kind of linear algebra system, it's something like that, right? So the idea is that computers typically deal with finite precision representations, and this lets you actually do things like integrate equations. So you can have mathematical functions and it will resolve them. So it can do simple things like systems of equations, but it also can do some pretty cool, more advanced things as well.
Yeah, and I use this quite often in prototyping. I work for the spatial stats team. We'll get academic papers in. We kind of want to verify that work or get a better understanding. So rather than me coding these things out and verifying them, I simply, kind kind of translate the equations directly from the paper into Simpie and change some of the parameters and let those run.
And this is, again, most of these packages are things that are included with Pro. This is one that's included in Pro and in ArcMap as well. So Matplotlib's been around for a long time in our stack, and it provides this basic charting capability. If you've ever used MATLAB, it feels very much like MATLAB. It lets you make MATLAB-like charts. And that has kind of two sides to it, right? They're not always, they're a little clunky looking, and the API is a little bit challenging to use sometimes. The nice thing is that this is available pretty much everywhere. Even the newer charting APIs that are available to you often will have Matplotlib as one of their backends, so they might use it internally. And sometimes it's nice to know the lower level pieces because the fancy thing doesn't work or there's some problem that actually is a Matplotlib problem.
Yeah, and one of the things that this points out about the SidePI package itself is that it is evolving indeed, but it's not taking any quick sharp left-hand turns. Is that over this 5, 6, 7 year period that it's been around, it's been stable. They're not pulling out this module and now saying Matplotlib is no longer part of the SciPy stack because we're on the bandwagon for this nice, neat new thing that came out this week.
Yeah, like I think a couple of talks this week have used like Seaborn, and there's some other really cool stuff happening in the Python visualization space. But actually, a lot of those same libraries use Matplotlib internally as part of their distribution. So if you're in Pro, you also have charts, right? You can make charts by hand, and you also can make them programmatically. And it can be handy to have that at times as well, right? The nice thing there, the things that we can do on the integration front. So if you, for example, if you run a tool it might generate charts by default and put them directly into your project. So there's some nice things that we can't do directly with something like Matplotlib. Okay, so Numpy is at the very base of this stack, and it's kind of the thing that lets you represent these multi-dimensional arrays. So it has a few different things it does. Really, the number 1 and number 2 really matter. Number 3 is kind of this oddball that it does random number generation. I think they needed random number generation, so they shoved it in. But the main 2 things here is that you have this representation of arrays. They're multi-dimensional arrays. They can be sparse matrices. They can have these different representations, and it knows how to very quickly do computational operations on those matrices. And if you've done a lot of problems in science end up boiling down to matrix manipulation. So this is really helpful, and this is embedded in almost every single library that you see. You'll find something new and you'll be like, oh, this is cool, and you'll probably see that they have a from Numpy array or to Numpy array built in, or they might actually, their objects might just be consisting of Numpy arrays internally. So we'll talk about pandas in a minute, but pandas is one of those things where all of the data at the bottom of it are in Numpy arrays. One of the properties of this that's really nice is that those Numpy arrays are stored down at the sea level, like kind of I mentioned earlier about how there's these bindings. Numpy is really one of those bindings. It basically lets you store in contiguous blocks of memory in C all your data, and then it quickly accesses through Python. So it's just a good performance optimization. If you're using ArcGIS, and this can be Pro, it can also be desktop or server, we have functions built into the product to let you take data in from Numpy and generate new data and put it into the SciPy stack, and then also take output from Numpy and put it back into our software.
Yeah. I use these quite often, is that I want to do the reading, the ingestion of the data in ArcGIS Pro. I just want to add a strange raster format to my map or a vector set of features to my map, and then I don't have to worry about writing the Python code in order to read that. I don't have to handle missing data values or offsets or anything, and then I'll just simply use one of these utility functions, raster to Numpy array, and then start doing my manipulations that I can't do in Pro.
There's also times where you might be saying, well, I want to use cursors, but can I get more performance? Numpy arrays are one way of doing that. You basically tell it, you create this header that says like, here's my fields, here's the data types of the fields, and you can really quickly then just send that on through one of these converters to get, so you could imagine that you're not using this side of the equation, you just are in here, you have your data coming from, whatever data sources, and then you generate the input to convert it all in one shot through one of these conversion functions. It can be a really good way to get really high performance out of data structures that aren't native to ArcGIS. And then SidePI is, we call it the Scifi Stack, but SidePI kind of does the things you actually might want to do with these Numpy arrays and not just store the arrays and do basic math. So it does things across all these different domains of science, lots of things that might be used from everyone from physicists to ecologists and everyone in between. And it has some cool, we're going to show a couple of really brief examples of using the statistics part of it, and also it has some multidimensional image processing. So there's kind of nice hooks here that you can use in your own work if you have certain kinds of use cases that aren't maybe directly represented in an existing spatial analyst tool or in our statistics tools.
Mm-hmm. And particularly with SciPy, you'll find a lot of cookbooks out there that are domain specific. So you can go and find some great cookbooks for atmospheric sciences that are based on the SciPy packages. So essentially at this point, you're letting SciPy do a lot of the heavy lifting for you, and you're not rewriting all of that code that's been out there and proven already.
Yeah, and it's really well-tested code. If you look at the method signatures for a lot of these, if you dig down, you'll see that they'll have really good, good academic references in most cases, and it's a nice library from that perspective. So here's just a really basic example, right? This is, someone asked me this, I think, on GeoNet a few years ago, like, I want to compute a geometric mean of a raster. I didn't even really know what that meant at the time, like, why, I knew what a geometric mean was, but not what it meant to compute on a raster. But this is all it takes to do that. So you basically, I'm feeding it here an input TIFF. I'm using one of those conversion functions that we just showed you earlier of taking a raster and converting into a Numpy array. And then I'm going to ask SciPy, it's the unfortunately namespaced stats.stats. I don't know, I'm sorry. But inside of stats.stats, there is a gmean method, which is the geometric mean method. And I'm passing it my Numpy array. And this last thing is a little bit tricky. This is something that if you get into Numpy, you'll find quickly, this idea of an axis. The axis is you have this multi-dimensional array structure. Sometimes you want to compute on a row basis. Sometimes you want to compute on a column basis. Sometimes you want to do things on depth. Sometimes you want to roll the whole thing up, right? So in this case, we're flattening it out. There's no spatial adjacency. In this, we're saying just unroll the whole thing. Just treat it like a big vector of numbers.
Yeah, but a caveat is that the functions only work if you do the associated hand movements with them.
Yeah,
So
hand movements are completely prerequisites. Yeah. I should have been a flight, what are those people called? Okay, so benthic terrain modelers, just wanted to give you a quick example. This is a Python add-in and toolbox for geomorphology. It's open source. We support it. We just published a paper about it last year. It has a large active user community, mostly marine scientists, but it works in the terrestrial domain. If you're not a marine person, you can still use it. It won't bite you. It supports things like ruggedness measurements, so the complexity of the terrain. It can do a variety of operations that could be of interest to you. So it has some lightweight SciPy integration built into it. So it uses ND image for multiscale analysis and Scifi Stats for circular statistics. So just a couple quick examples of that. Here's us doing some, let's see, this is the, actually, I don't think I can see the rest of the code example. I will fix that in the slides that you see. But here we're just going to do a conversion. And if you could see the rest of this, let me actually just jump out really quickly here and see if I can find you the actual underlying code there. Let's see. Oh, that's all it is on that slide. Okay. Okay, sorry. I split this example over two pages because it wouldn't fit on one. All right, I've got to jump around here for a minute. Let me get back to where we were. Okay, so this is the first part. We're taking in an input raster, and we're going to just sample a little corner of it. So you can see here that we're doing the same thing, right? We're doing raster to Numpy. We're taking our input data set, raster to Numpying it. We're taking that input raster, and we're just going to clip out a 200 by 200 little chip out of the top corner of the raster. And what we're doing here is we're doing sampling for multiscale analysis. So we're going to take that and we're going to plot that little, we're going to set up a plot that's going to have a 10 by 10 matrix for us to output rasters into. And then we're going to go stepwise through that data, and we're going to run a median filter at different scales. So this is like if you do focal stats, exactly the same thing as focal stats. We just get a little bit of extra tweaking that we can do here that we can't directly do with focal stats. So here we're going to just compute that. We're going to start out at our initial scale, and then we're going to keep going at lower and lower resolutions. And we're going to add a new plot at each of those different scales. And you can see here that we're running this median filter, and we're passing it the size that's being used in this for loop. We're computing a size out of that value that the for loop is fed, and we're going to compute 25 of these little things on this 200 by 200 pixel block. And once we do that, we get something that looks like this, where we can see. So you have this. This is a bathymetry data set, but you can see like at the really the high resolution scales, we see all this really fine-grained, detailed patterns. And then as we get all the way down here, we get just down to this kind of general trend. And this is useful in some contexts where you need to find features at certain scales. You can use this kind of multiscale analysis to pick out appropriate scales for doing other kinds of computations. So there's certain kinds of things where you have to go and you want to generate these covariates and you want to do them at special scales. You could use this if if you've done some diving in this area and you know that, well, there's this kind of feature here and that matters for this particular species I'm interested in. Then you could say that's a potential scale that we would be interested in. Or you can just do a computation at all the scales and then try to let the math, walk your way out of it. But sometimes you want to actually only work at specific scales. Okay, so that's one example. Okay, I guess, yeah, the text is not quite the right size here. Another one is circular statistics, right? So if you have a variable like time or season or anything that has this circular component to it, you can't use a normal statistical method, right? Because if you have a value that's at, 359 and another value that's 1, you're going to get the wrong thing if you average those things. This lets you break it down. This is a very simple technique. It's not going to win you a Nobel Prize, but basically it's going to take that single circular variable and decompose it into two components, the cosine of the value and the sine of the value. So this is a very simple technique. So aspect is one of these circular variables. And so this allows you to just take an input aspect data set and then generate these two outputs. So to see this with SidePI, all we need to do is we take our input, and you've seen this pattern now a few times, with the really important SciPy.stats.morestats, not just stats this time. Sorry about that, but the namespace isn't great. And with more stats, we do get these circular, we can ask for a circular mean, a circular standard deviation, and a circular variance. So it can compute these values for us directly. Okay, just a couple other little things in the box. These are just almost like Easter eggs that I wanted to mention. One is that, so there's something called IPython. If you right now, it's in muscle memory for me to just type in Python. But I'm trying to break that habit because if you're using Pro today, you have better options available to you. I'm not actually going to, I won't show you a demo because it's not really worth it. But all you do is say Jupyter space console. And what you'll get is you'll get a REPL just like you would normally with Python, but it's augmented with a bunch of other really great stuff. One of them, just to start you out, is this thing called the run command. So you say %run space the name of your script, and it will run your script inside the REPL, inside that normal Python window you're used to. It will evaluate the result, and then after that, you have all the variables, all the stuff that was set up in your code is already configured. And if you go back and you edit your code and run it again, then you can change it. So it's a much simpler way of doing things. It has a bunch of other really nice features, like a history feature. It has just 10 or 15 bells or whistles that you won't get with the default Python interpreter. There's also one called IPython. They're pretty similar. There's a couple extra things in the Jupyter console, but check either of them out. They're actually in, IPython's in the program group for Pro. And if you can break the habit of typing Python and just type IPython, I think you'll find that it has some really cool features in it. I use the history all the time too, because you can type %sign history and get all the code that you just typed recently, similar to you can have in the Python window in Pro or desktop. And Jupyter Notebooks, I think you probably have seen Jupyter Notebooks at this point. Can I get a raise of hands of who has not heard or used Jupyter Notebooks? It's okay. It's totally fine if you haven't. It's not okay. I think most of you have seen it. I'm not going to belabor the point. I'll show you one new cool thing with Jupyter Notebooks at the end of this, something that's coming out soon. But yeah, they're really useful, and they're a new modality. That's one thing that I think we like to emphasize, that it's not just, sometimes people say, oh, well, I have notebooks, so that's all I'm going to use, nothing else matters. And it's like, it's not quite that way. It's still the case that it's really useful to convert your code into functions and to make modules, and it's still useful to have scripts. You still need an editor to write just code that's in regular Python files. And you also need like a REPL like IPython or Jupyter Console or just a regular python.exe, because sometimes you just want to quickly type something, see the result, or the Python window, the same kind of idea. So we see it as being an augmenting experience. It complements some of the other things. Obviously really great for things, educational things, and there's a number of contexts it's really great for. Okay. So now we're going to dive into one of these libraries. Pandas, you probably have seen if you haven't used it yet. It's very widespread. The idea here is there's a guy working at a hedge fund, and he's like, I want to use all this cool stuff the R people have, but I want to do it in Python. So there's this idea of this panel data, there's data frames that are in R, and he basically ported that to Python. So it brings this kind of more robust data analysis pipeline to Python. Data frames are really great. They came from a scientific community, but they're useful for so many things. And they're one of these things where, like, when you first look at them, you're like, that's a table. Like, I already know Excel. This isn't impressive. But it turns out that by just adding a few additional things to that model, there's a lot of power that you can get from that. So one thing is that it's labeled. That means that the different columns in it have data types bound to them. And it also has indexes built into it. So that really helps with performance and some other characteristics. And I have a very simple example here, and Kevin's going to actually show you this, but I really like to show The Simpsons. So here's some data from The Simpsons. I'm reading in with Pandas a CSV file that has the ratings on a per season basis. For a while I was obsessed at when did The Simpsons jump the shark? When did it go from being great to being terrible? Because at some point that happened. And so I started using this data to look at that question. And one way you could look at it is Nielsen ratings. And unfortunately, I found out that Nielsen ratings aren't a good way to look at anything, because they constantly are changing their sampling mechanism, and there's all kinds of problems in their data. But we can read in the data that we do have on The Simpsons and ask it some questions. So if we just read in the CSV, and then we ask the pandas data frame, once we've read the CSV in, it's converting that into this data frame representation. We can do things like ask it, what columns do you have in the inside of this data frame? So it's gone and it's applied these labels to the different column headers it detected, so things like season, households, the TV households, and it's just labeled them so we can access them quickly and use them in other ways. And then the thing that's really great about data frames, and this is a very, very rudimentary example, is that without having to write SQL or having to, say, like loop over every different entry in our data set, we can just ask it questions. So we can do something like, I want a new data frame. I want it to be called Majority Simpsons. I'm going to look at that data frame we just made, and I'm going to ask you for all the values where prime time percentage, the percentage of households who watched The Simpsons during that year, exceeded 50%. So this is back in the day where that was like physically possible. Now it's like, probably like 3%, and they're really excited. But these are the seasons where that was true for them. So now by doing that, we've basically asked it, we've done this filtering operation, and we've bound it back to a new variable. And now we have two data frames, our original data frame, and we have this new one, and we can do that same kind of aggregate analysis there. And it supports a whole slew of additional operators that Kevin will show you more than I will right here. I also want to mention that this is the basis of the spatial data frames object. If you've seen the ArcGIS API for Python, that's built on this same model. It's augmented with geometries. It uses ArcPy internally for a lot of the things that it does. It's continuing to expand. This will be a growth area. I think if you invest time in pandas, it will serve you well. We're still looking at things to make this story even better than it is today. And with that, I'll turn it over to Kevin.
Let me move a little more.
Okay. Are you on? You're on 4?
Yeah.
Is it? You want me to go out front and see if it's there? Okay.
There we go.
Great.
Okay, I want to show a quick example of pandas. I'll start with doing some quick imports. I'm not a trusting person and need constant validation, so I printed out the versions of pandas and Numpy that I'm actually using. So I want to analyze a data set today that's from the US Department of Transportation. This is a 10% sample of all airline tickets in and out of the United States. A tremendous data set. I think there's a lot of opportunities for market research here, for trend analysis, for looking at natural disaster-based migration patterns. And so just a tremendous data set. It comes from the US Department of Transportation. I downloaded it as a CSV file, and I want to be able to read that. And I'm going to use pandas in order to do that. You can see I read a fairly large file. That file was zipped. I didn't even have to bother unzipping the file. And so it looks like I've got about 168,000 records here for just this period of time that I'm looking at. I'm going to take a quick peek at that. And as Sean indicated, columns are labeled in pandas, so I get a good idea of what I'm looking at. And I can see lots of airport codes here, lots of additional data that I'm not interested in. So I'm going to quickly reread that and limit it to just the passenger count, the origin, and the destination airport. Now when I look at that, I've got a much more workable data set here. So I've got origin and destination airport. But again, I've got thousands of records here, and I can't discern any patterns. So I want to take some quick stats of that. And I can see some of those origin destinations have 0 passengers for some reason. And so I'm really only interested in airports that have a lot of traffic in them. So I'm going to just run a query against this and only get airports that had more than 10,000 passengers in a year. I didn't have to reread the data. I'm just running a query against that data. And now when I look at it, I can see that I've got a minimum of 10,000 and still my maximum. So again, that's nice to summarize that table, but it's still not really in a workable format where I could use it to make some decisions. So what I want to do is, because this is monthly or sometimes even daily data, I'm going to compress that down. I want to group it by origin and destination so that I get a single record for each origin and destination, and I sum all of the daily or monthly passengers into that one record for that origin destination. I did that pretty quickly. I can see this looks like Albuquerque to Atlanta has a fair number of passengers. What's my largest there? Albuquerque to Phoenix. I wouldn't expect that number to be that high. So again, still this is in tabular format, but probably to be useful or to include in a report, I'm probably going to want to represent that as an origin destination matrix, and I can just do that with a pandas pivot table functionality. And I have that, but you can't get to every airport from every other airport, so my matrix has a lot of nans in it. I'll just run a quick function to clear that. And now for this period, I've really come up with some useful information that a decision maker could use in a few lines of pandas code. And what this really falls under, the category of, in my mind, is what data science does is it lets the machine do the work. As data scientists, we're interested in solving problems, and we'll use any tool or we'll offload the work to different libraries in order to get that done. Is that as data scientists, we are people that integrate lots of things together.
Yeah. So I have a quick slide on that. We'll stay on your machine.
Okay.
So basically just what Dask is, one of the things it provides you is this massive data parallelism through Python. And one of the ways it does that is by computing graphs on the underlying analysis. So if you have something that's trying to do a bunch of work, it figures out, hey, these pieces of this work can actually be independent, and that might be sending that work then out to different cores on one machine, or it even could be across some heterogeneous set of computers, and it knows how to do that. And instead of showing that slide, I'll just let Kevin jump right into his demo of it.
Yeah, so I'm new to Dask, so any really difficult questions, I'll go to Sean. But in just the short period of time that I've been working with it, I see where, for me, Dask is the solution to big data. And it's the solution for parallel processing for a really lazy programmer. Because it does the work for me. Numpy is great, but Numpy arrays must fit into memory. And that's not always the case as we're working with bigger and bigger data sets. So let me show you some of the functionality of Dask. Again, I've got this, let me just clear my cells here real quick. I've got this collection of CSV files on my disk. I happen to just put 30 here. I could have hundreds of thousands of these CSV files. And if I were going to read those with pandas, what I would have to do is read one of those files at a time, okay? And that's time consuming. I would have to create a loop through those, find some way to append those together. But with Dask, it mimics a lot of the functionality of pandas, but it does it in a parallel nature. It automatically parallelizes a lot of the pandas functionality for you. So now I'm going to read these into a Dask data frame. And I just read all 30 of those files in 31 milliseconds. And you look here, you can see that Dask actually parallelized that operation for me. I want to as you see up here, this data set contains some names, some XY locations. I want to summarize that again by name. And so this looks very familiar to the code that Sean showed you multiple times. It looks very familiar to the code that I showed you in the pandas demo. And that is, again, in this SidePI Python environment, you don't have to relearn patterns. They tend to mimic each other. So in this instance, I'm going to do this summarization. About 2.57 seconds. It's summarized by each of those. Not too bad. This also lets me go out to a format called Parquet, which is a very fast format to read and write. Again, as the size of problems, the size of the data that we're analyzing as data scientists isn't getting any smaller. It's just growing and growing and growing. So we're always looking for faster ways to do this. So I output this to Parquet, and then if I reread that back in, I read that entire data set in about 52 milliseconds. Very, very fast format. So to show you how Dask handles big arrays, I'll see if I can get this demo to work on my clunky little laptop here. What I'm doing is I'm creating a 10K by 10K array, and I'm just doing it in Numpy. So that's just we're in the past. We don't have Dask. I want to create this array, and I want to do a dot product on it. Okay? It is running. I'm going to trust that it's running. About 7.3 seconds, not too bad. So that's not a huge array. Now I want to do the same thing, but I've got a much larger array here. What's going to happen? Memory error. I can't fit that into a Numpy array. And so now what I have to do? I now have to stop thinking about the problem that my employer is paying me to solve, and I've got to go back and start writing code to chunk this thing up just so that my machine can run it. So let's try the same thing with a Dask array, okay? I'm doing the same exact kind of operations, but this time I'm just going to say create the same huge array, but I'm going to chunk it up. I want Dask to automatically chunk this array up. I don't have to worry about the chunking. And I must not have run.
Is there an import up above maybe? DA task.
What did I not run, Sean?
Is there an import task as DA?
Nothing like coding in front of people. Still not right.
Has no attribute random. I'm not sure. Look really quick.
These, of course, worked perfectly in the hallway when I ran.
You could try running all cells and see if it was something up above.
Yeah.
Creating random. Is it dask.array?
Oh, I don't know what it did, but it seems to be running now. I'm not going to let this finish. Oh, I got a memory error that time too. No, that's the Python one. Okay. Well, trust me, it does indeed run, and it does take a while. You know, Dask is not going to automatically turn your desktop into a supercomputer, but I can acquire an array of that size.
And like we mentioned too, this actually could be running on other machines. It could make SSH connections, do different things to actually have this be across multiple machines in the same. You don't have to actually change your code other than configuring it to have this pool of computing behind it.
Right.
Yeah.
Okay. So, and as Sean was saying, these is automatic multiprocessing essentially. So you give Dask a series of tasks. In my case, the task was just those chunks of the array, and it processed through it. So if you're curious to know how is Dask actually doing this multiprocessing, you can actually ask it to print out that multiprocessing graph that it's using to build these connections between. And I won't interpret this for you, but you can see, and particularly when you get into more complicated tasks, you can make sure that Dask is doing a good job of actually sequencing the different portions of your code. It's been an interesting introduction to Dask for me. I think I'm going to rely on it heavily in the future.
Yeah, and it's included in the hosted notebooks platform, so you can use it there immediately. You can also conda install it. It's an easy one. I'm going to skip. I have some things about where can I do this and how fast is it. The short answer is you can use this a lot of places, and it's pretty fast. You can look at those slides later if you want. There's a couple things I want to show you and also leave some minutes for any questions. So a couple things that are coming out soon. Hosted notebooks you've probably seen. You've probably seen some of the things that are deep learning in Pro. There's some things already there today. There's more coming. There's ArcGIS.learn, part of the ArcGIS API for Python. That's backed on top of a library called PyTorch. There's also notebooks in Pro. And I'm going to show you just I just demoed this in another session. I'll just quickly show you what that looks like. And we're also supporting ArcPy in external Conda environments. So the idea there is you might work with someone who, they do have Pro on their machine, but they already have existing environments set up through Anaconda, through different things. They can directly access that they can just Conda install ArcPy and have it work. So this is that Conda installing ArcPy. You can see I'm using Anaconda Navigator. I find the ArcPy package, and I click on a button, and I install it. And all this takes is Conda space. You can use it through the UI or Conda space install -c Esri space ArcPy. So you ask it to install it from our channel. And there's a tech preview of this available today. This will be actually shipping in 2.4. And this also means that you would be able to use ArcPy across different versions of Python. So you could have a different version of Python than the one that's driving Pro. The other thing is, this is something we just demoed in the Road Ahead session. This is notebooks inside of Pro. So the idea here is that you could use this with something like the hosted notebooks. You could view your notebook and it's in Pro, but you actually can interact with your map. So in this, you can't really see very well in this picture, but basically I'm importing the ArcGIS API for Python, and then I'm going to go and I'm going to search for some content. And I look and I find that, oh, here's a feature layer that I'm interested in. I can click on it. I can render it just directly inside of Pro, just use it like a web page, confirm, okay, this is actually the data that I'm interested in. But the nice thing that this really gives you is that, okay, now I want to actually use this as a data source in my map, right? Often if you're in Pro, a map is a big part of what you're doing. So now I can just take that layer and I can ask it for its underlying URL. And then using just the arcpy.mp module, I can add that layer to my map like anything else, right? I could update its symbology. I can do all those other things I can do with Pro, all in this one integrated context. And the nice thing here is that I can then, on that data, run tools. Here I'm running a density clustering tool. And I can generate new outputs, and I can do things like make charts that are the charts that Pro supports, and get all the other really kind of rich capabilities, right? I could add a new table view of that data. I'm not bound just to what's available to me through the notebook itself. Okay, and I think that's it for content. With this whole resources section, you can look at that later. Thanks to all the great folks who have participated in this work. And if you feedback, iOS or Android, submit it. If you have Windows Phone, I'm sorry. We only take cuneiform tablets, Akkadian preferred. And I think that's it for us. We'd like to take any questions.
Yeah. Or we'll be around afterwards.
We'll be around.
If you have
That's fine too. Yeah, thank you for coming.
Yeah.